Hey everybody, welcome back to Young Engineers of Today. I hope you're ready to continue with the Raspberry Pi. Hey, bud. Um, because that's what we're going to do today, and we're actually going to go more on the programming side of things to complement the hardware side of things. So, if I believe so, we should have done that already. Yeah, we moved the the jumper cable over to GPIO 17, if I remember correctly. Anyway, yes. So on Tuesday, we set it up so that the Raspberry Pi would provide constant power to an LED, certainly at first. And that gave us some familiarity with the way a circuit would be set up and how all of that would work. Um, it was a very simple circuit. All it was just power from the Raspberry Pi. It was going through the LED and then through a resistor and then back out to ground. Nothing crazy there, no surprises. We just had a light up LED at the end. And it was lit as long as the Raspberry Pi received power. Presumably, if you're using fritzing like I was, you can't simulate the circuit, unfortunately, but that's what it would have been doing, um, you know, had you been able to simulate it, or if you were able to do it physically with an actual Raspberry Pi and an actual breadboard and everything like that. Now, that's one aspect of it, but what we were interested in doing was making it so that the Raspberry Pi could make the light blink. And so rather than just hooking it straight up to one of these 5 volt or 3.3 volt power pins, we moved the connection over to GPIO 17, which is also known as pin 11, which is this one that's about 6 down. Um, and that's where we left it last time around. We just left it so that it was this circuit essentially, except that particular jumper was hooked up down here, or 1, 2, 3, 4, 5, down here. Beep, that one right there. But if we were to provide power to the Raspberry Pi, it would not light up that LED. And that's because there is a whole secondary aspect to that involves programming on the Raspberry Pi. Like I was saying before, there's a programming side and a hardware side that sort of go hand in hand in order to do this automated aspect, this sort of microcontroller aspect that the Raspberry Pi has. Physical computing is the uh, popular accepted term for it. So while we touched the hardware side, we never touched the software side. So basically on the inside of the Raspberry Pi, it's not getting a signal to send, well, a signal out on that pin. So from our perspective, nothing is happening because nothing's actually happening. But that's okay. Today, that's all going to change. We're going to set it up so that the Raspberry Pi will send a signal out on that pin, making the LED light up. And on top of that, we will set it up so that the LED blinks. So it's going to be more than just what we had initially, which was the Raspberry Pi providing constant power to an LED. Because, being able to make a thing do something in a pattern is certainly more interesting than just having it be on all the time, as we all well know. So in this case, we would be utilizing the Scratch program on the Raspberry Pi. For this part, I'm actually going to go through the slideshow because, again, my Raspberry Pi is not working, unfortunately. So I can't bring it up on the network in order to show you guys how it happened on a Raspberry Pi. On top of that, the online version of Scratch does not have the same sets of commands because it's not a part of Raspberry Pi that has GPIO pins. So all of the GPIO commands don't exist on the online version of Scratch. It's unfortunate, but this is the reality that we live in. So the whole idea, as I've mentioned a million times now, is it would be, our goal is to have an LED blink, to turn off and on an LED without disconnecting a wire. So using the Raspberry Pi to control it. So we would be using the Raspberry Pi Scratch. And let me go ahead and open this up in presentation view so you guys can see it more easily. It does say here on this version that you would want to open up the control category. Now, why would you want to open that one up first? Why would you think? Why might you think? What would be the first thing you'd probably want to include in your Scratch program? If you know, just go ahead and throw it into the question box. Why would you, if you're setting up a program in Raspberry Pi, oh yeah, you definitely know, Ben. Uh, the question initially was, if you want to create a program in Scratch, why would you go to the control category of blocks first? Like, what would be the first thing you would place in a Scratch program, whether or not it's for the Raspberry Pi or for the MIT Scratch website? Exactly. You know too, Ved. Yeah, I mean, basically, you guys all know. It's the when green flag clicked. Obviously, you need a start point for your program, right? You need some place where everything begins. So that might be something that pops up in your debugging. When you're doing this competition, you might be sitting here looking at a program and it's like, oh, this program doesn't run. What's the problem? And you would be surprised when you assume something as simple as that in a program. Obviously you need the when green flag clicked, because otherwise your program won't run. You might be sitting there looking at the flow of the program, trying to figure out how everything works, and whether or not, like, maybe it is running, but like, it's waiting for an input from something, and that's just never happening, and blah 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 blah. And then you might spend, I don't know, 2.5 minutes looking at it, and then you look at the top and you see that there's no when green flag clicked block. That kind of stuff. I mean, I'm not saying that there will be a question like that specifically. I'm just saying that don't be surprised if something like that comes up, because I can't tell you how many times I've been working on a program and being like, why isn't it working? And then I realized that I forgot to include like the start conditions or something like that for a specific piece of code. Nested in an if statement and actually provide a set of conditions for it. I got so engrossed in writing what actually happens when those conditions are met that I forgot to include the conditions. And it'll if you continue with programming, it'll happen to you too. It's just an inevitability. Sometimes you get so involved in the details that you forget about some of the simpler stuff at the beginning. So yeah, we would add the when green flag clicked block. Then you would utilize the broadcast command. Do you guys remember the broadcast command that we used maybe like once or maybe twice when we were looking at Scratch? Okay, so I got a couple of yes. How do you connect wires to the GPIO and Raspberry Pi? So like I was saying on a Tuesday, it's possible to use an alligator clip, although it has to be a very small alligator clip. However, there are female to male jumper wires, and those would be ideal probably because the female end could plug into the Raspberry Pi and then the male end could plug into the breadboard. And those would usually be your best bet for connecting wires to the GPIO and Raspberry Pi. Although, yeah, it is also possible to use alligator clips if you need to, because alligator clips are made of conductive material. That's their whole point. They're meant to connect two things that wouldn't normally connect, like two sets of wires or something like that, and they're conductive in order to allow that that connection to exist even through the alligator clip. So yeah, you could use that as well. They just need to be very small ones because, as I'm sure you guys have noticed just by looking at your Raspberry Pi, those pins are very close together. So you want to make sure that the alligator clip isn't touching another one of the pins on the Raspberry Pi, because you could get garbage values. You could accidentally send electricity back into the Raspberry Pi when it's not supposed to be receiving electricity, that kind of thing. It could be unintended results. But yeah, for those of you who don't remember about the broadcast aspect basically just sends a, I guess it sends a message. GPIO send a message. Oh, sends a message to all sprites. Yeah. No, you're fine. You're fine. Yeah, you basically hit the nail on the head. It sends a message to all the sprites, and there might be sprites that are listening for that particular message, in which case when they hear that message, they'll do whatever code is attached to the flag that listens for that message. Um, however, and that's how it normally works. However, on the Raspberry Pi um, Scratch, there are actually it's a way to send a message to the physical computing part of the Raspberry Pi. That is to say, the pins. So when you say broadcast and then GPIO server on, what you're saying is, hey, get ready because we're going to be using the GPIO pins in this program. So the Raspberry Pi essentially primes the GPIO pins. It sets up a few routines that watches them and listens to them and gets ready to send messages out on them. It pulls up a whole list of commands that you can utilize so that it understands what you're talking about when you want to send a command out and stuff like that. It sends a message to all variables. More like it sends a message to the CPU on the Raspberry Pi. You can think of it like that. This particular, like normally a broadcast would send a message to all sprites. This particular broadcast, this particular command will send a message to the GPU, or excuse me, the CPU on the Raspberry Pi. So you can think of it like this. You're actually talking with the CPU. You're hacking. You're hacking. Not really, but it's kind of fun to think of it that way. So GPIO server on, what that'll do is that'll basically just prime the Raspberry Pi and get it ready to be to use the GPIO pins that exist on it, and that involves a number of things. Then we've got another broadcast message after it, labeled config 17 out. I was going to ask why exactly 17, but it basically explains that on the slide right here. The reason why we're using 17 is because when I had you guys set up the circuit on Tuesday, I had you connect this circuit to GPIO pin 17. And that's an important thing to note. So when we're looking at this, yeah, exactly. Send an output message to the GPIO pin, through the GPIO pin, in fact. Well, you're telling the GPIO pin that it is an output pin, essentially is what's going on there. But you haven't sent any messages yet, but you will be. You're telling the Raspberry Pi, okay, so pin 17, GPIO pin 17, that one's going to be an output pin. So anytime we talk with it, we're going to be sending messages out on it. But yeah, so that brings up an important point. If we look at this diagram, we've got two sets of numbering for these pins. They have their names, and then they have their pin numbers, which is different from the redundant term referring to the number you entered in an ATM. This is actually just referring to the number of the pin. So you've got pin 1, pin 2, pin 3, pin 4, pin 5, pin 6, blah, 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 blah. And then you've got 3.3 volt power, 5 volt power, 5 volt power, GPIO 2, GPIO 3, blah, 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 blah. So we're referring to GPIO 17, not pin 11. So anytime you're referring to the GPIO pins in the Raspberry Pi Scratch interface, you're referring to the pin names, not the pin numbers. Now, that can be a little confusing because the pin names also involve numbers since there are so many GPIO pins. So that's why you have GPIO 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Where's 14? 14 isn't on here. 15 isn't on here. 16, 17, 18. It's all over the place. It's a mess. It's a mess. And part of that just has to do with the fact that, I don't know. It's probably because they're all given the name GPIO something or other, but they're some of them are not actually GPIO pins, and it might also be related to how they're actually connected to the CPU. It might be that GPIO 8 is actually connected to an earlier an earlier pin on the CPU than GPIO. Let's see here, 9, even though 9 is pin 21 and 8 is pin 24. And that's why they want to stick with the. It's one of the reasons why they want to stick with the pin names as opposed to the pin numbers, because uh, it could not exactly line up with how the compute, like it might work better with the order that the pins are connected to the CPU, and B, by saying config 17, there is the fact that we can only use GPIO pins removes any doubt. We don't have to sit here and be like, okay, is pin 17 a GPIO pin? We know that it is because we can only talk to GPIO pins. And we know in this case that it's going to be GPIO pin 17 as opposed to pin 17 because we can only talk with GPIO pins. What are the reserved pins? The reserved pins are usually pins that are, reserved. It could be that they're meant for testing. So like when each one of these Raspberry Pis is manufactured, usually they go through a battery of tests in order to ensure that all of the circuitry is functioning nominally and everything like that. So reserved pins might be reserved for testing. It might have a machine that hooks up to those pins and sends and receives a bunch of data in order to see whether or not it's returning like the proper commands. It could be that it's reserved for factory resets, or it could be reserved for the timing chip or something like that. Reserved could really mean any number of things. In this case, the door is a little bit close to us. There's a veil over the window. We can't exactly look inside and see exactly what it's reserved for, but yeah. Would Scratch recognize specific messages, or are we just naming the message? These are specific messages that the Raspberry Pi and the Scratch version of Raspberry Pi recognize. Like, we're not just calling this config 17 out for our health. The specific sequence of keywords, config, a GPIO pin number, and out, are recognized by Scratch and by extension the Raspberry Pi as a specific, specialized, reserved command for the Raspberry Pi. If we want to make a GPIO pin output, we need to use that specific message, config GPIO pin number out. Same with GPIO server on. GPIO server on is a specific reserved message for the Raspberry Pi to turn those GPIO pins on and start listening to them and talking with them. So, we couldn't just say like, hey, turn pin 17 out or something like that. Like that wouldn't make sense to the Raspberry Pi in that sense. It would be a perfectly valid broadcast message, but it would be more like a traditional Scratch broadcast message that would send a message to all of the other sprites, and then those other sprites would need to be listening for that specific message. This is not something we could use in order to set up a GPIO pin on the Raspberry Pi. We would need to use this message. So config 17 out makes GPIO pin 17 an output. And then you would add a forever loop, which would actually be a pretty important thing. Why would you want a forever loop? And why would it not be around config 17 out? What's up, Ved? Are you not sure? Or are you not sure what the question was? Well, yeah, so we can do things forever. Yeah, definitely. Why would it not be around? Oh, gotcha. Not sure what the answer is. Okay, I get you. Why would it not be around those top two commands though? What do you think? Just like stab in the dark, you know, you don't have to know the answer right now, but take a moment to think about what those commands specifically do and why they're not maybe embedded in the forever loop. Well, we do need to respect code, yes, and it can't turn on forever. Okay, so you're getting to the root of it there, Ved. Think about what you said there though. Where can we find all standard commands like config out? That's an excellent question. I'll see if I can't look that up for you. Oh, repeats. Oh, I mean, we also need to respect code. It's a good thing to do, but just not abuse code because that's bad. But yeah, repeat code. Yeah, we blah, 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 we do. But specifically, I'm asking why aren't we repeating those first two commands? So think about it this way. This is a little yeah, it does. And so it goes a little something like this. Yeah, exactly. That's actually exactly what it is. We're initializing these, and we don't need to continue to initialize them. You can think about it like this. This is a little bit bleak, but you know, bear with me here. So you guys are students, right? You guys are students in a specific grade. You can think of the school year as a bit of code. The first bits of code establish what grade you're in. Then you got a second bit of code that's in a forever loop. And inside that forever loop, you've got, you know, go to class, do homework, take tests. Again, pretty bleak look at this sort of thing. But um, if we were to basically run this code, it would run something like you are in 8th grade. All right, we've established that. Now we get into the forever loop. You go to class, you do homework, take tests. Go to class, do homework, take tests. Go to class, do homework, take tests. Blah, 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 over and over again. Imagine we put that you are in 8th grade inside of the forever loop. Now imagine you're living that life. You walk into, like as you walk into class each morning, somebody goes, you're in 8th grade. And then you go to class, and you do homework, and you take tests. And somebody goes, you're in 8th grade. And you go to class, and you do homework, and you take tests. And they go, you're in 8th grade. And it gets really old, right? Like you kind of knew that after the first time. You don't need to have it be reestablished. So what we've done is we've established the starting conditions. We've established that the GPIO pins should be turned on and that GPIO pin 17 is an output pin. We don't need to keep establishing that. We don't need to keep setting that up every time. We just need to set it up once, and then we need to utilize that throughout our program. So for that reason, those things only need to be done once. I saw the sad face there, Johannes. I'm sorry. I know it was a very depressing look at coding and school. I didn't mean it like that, but it was the best analogy I could come up with on the spot. But yeah, so essentially, we only need to set that stuff up once, and then we can take advantage of that in a forever loop. But we don't need to initialize these variables every single time. So inside of the forever loop, we would put broadcast, another broadcast, it's a lot of broadcasts, GPIO 17 on. Pretty self-explanatory, right? GPIO 17 on. What we're doing here is we're sending a message to turn GPIO pin 17 on. Send a signal through it. It's literally that. It is to turn it on, like flipping on a light switch. So it will send electricity through GPIO pin 17, through the jumper cable, through the LED, through the resistor, back out through another jumper cable into the ground. And we will create a circuit. It will turn on. We will turn on the lights. Then we'll broadcast GPIO 17 off, and that will shut the power off on the pin, thus cutting the power on the circuit. Oh yeah, what was it? The final question or the ultimate question? Um, Something like that. The one with all the supercomputers. Last question. Thank you. That was what it was called. Um, I like that one. Anyway, we cut the power to the LED. The LED turns off. Why do you think those wait commands are in there? Yeah, basically. I've been there before. Just have your fingers on the wrong keys. No worries. Just do the just what was the final part of that sentence? Just skip over the doesn't and continue as if it never happened. Because I'm interested in hearing your answer. Okay. All right. There you go. Yeah. That's another possibility. Yeah. Yeah. You got it too, Ved. Yeah. So like, imagine you had a friend, right? Imagine you were friends with the Flash, and you were just kind of like, "Hey, the Flash, I want you to do a thing for me," and they're all like, "Sure, because I'm the Flash and I'm a good guy. I'll do that for you." And you go, "Okay, I want you to turn on the light, but literally the moment that you've flipped the light switch up, I want you to turn it back off again. And literally the moment you have flipped the light switch back off, I want you to turn it back on again. And I want you to do that over and over again, forever." And the Flash goes, "Okay, easy enough. Pretty simple." So he turns the light on, he turns the light off, he turns the light on, turns the light off, turns the light on, turns the light off. But the thing is, he's the Flash, so he does this several thousand times a second. That would be unpleasant to be around. So maybe you tell him, "Hey, maybe don't do that. Maybe chill out a little bit and at least leave the lights on or off for a little bit of time because I know you perceive time differently than I do. I can't turn a light switch on and off fast as you can, and a lot of times I'd like to keep it on for longer anyway." And he goes, "Okay, how long?" And you go, "1 second." So he'll turn it on and wait 1 second, and he'll turn it off and he'll wait 1 second. Turn it on and wait 1 second, turn it off and I'll wait 1 second. And suddenly this is a lot saner. This is not, you're not sitting here in an EDM show or something like that. Um, yeah. Um, and it's a lot more pleasant to look at too. So yeah, so it doesn't strobe, it doesn't, it doesn't send the command at the same time, which is to split hairs there. That's technically an impossibility because electricity travels fast enough that it wouldn't be a simultaneous command. To our eyes, it kind of would be. Um, Sort of kind of almost like just like with the fact that it would be strobing would mean that it wasn't a simultaneous command, but like the it would be very close to it. And yeah, it's possible that maybe it might overheat. Like probably probably not, but you never know with these kinds of things. It could be that that there is a power spike when the Raspberry Pi sends out power. It might be it tries to send out 3.3 volts on a pin, but for the first just like slightest instant when it sends out power, there's a quirk in the circuitry that makes it send out, I don't know, 5 volts, whatever. And your components would be able to handle that for that very short instant that it happens. But if you're if you're making that instant occur several thousand times a second, or like several hundred times a second, certainly, then it would be kind of like you're sending 6 volts constantly to the, or 5 volts constantly to the components, and that might burn them out. So yeah, I could see that would be a possibility, you know, or overheating them. That could definitely be a possibility. Again, assuming that sort of situation would be what happens. So mainly we do it so that we can actually perceive with our human eyes, on special eyes. Um, I don't know what that vague accent was, but anyway, um, we can actually see it turn on and off at a rate that, you know, kind of makes sense. Um, Notice that there's no command for like blink. Like we can't just say, hey, make the light blink. Um, there's very explicit commands: turn it on, turn it off, and we need to pair those in order to have it blink. A computer takes things very literally, because computers are, well, dumb, as I think I've told you guys about before. But yeah, computers are dumb. Computers can do math so very, very well that it makes our head spin, but they can't infer or assume or reason or anything like that like we can. So for that reason, everything's broken down into very simple, very explicit steps. And we have to think like that and utilize those very simple and very explicit steps. Yeah, they can only do what they're told, in order to get the desired output. So we'd need to pair it off with an on in order to have it blink, unless we teach them how to do it themselves. And that's actually what a lot of people are getting paid to do and trying to get their PhDs for and things like that. That is a pretty big area of research. Yeah, who knows how that could be. But yeah, so that would be the full program. It's a very simple program when you look at it. When green flag is clicked, turn on the Gpio pins, set Gpio 17 to be output, and then from then on, from now until forever, as long as the Raspberry Pi has power, turn on Gpio 17, wait a second, turn off Gpio 17, wait a second, and then just over and over and over and over and over again. And this, in essence, is kind of the structure of like an Arduino program or something like that, you know? Um, it'll have a very similar sort of set of commands that run once, set of commands that run forever. Like that's just pretty much every Arduino program. Um, and I think actually next year for Amazing Mechatronics, they might do something that's closer in emulation to an Arduino for you guys too. But like still very similar to Scratch. What programming language does the Arduino use? It uses its own programming language, but it's one that's very similar to like C or Java, syntactically, as far, and by that I mean, you know, the way the language looks and the sort of structure of it and everything like that. There are differences um, between those 3 languages, and Arduino versus, you know, Java and C, but they do look similar. Is the Arduino based off of processing? Um, Sort of, kinda, if I remember correctly. Processing has more of a... Oh, no worries. Hold on, let me look at the processing language again, because I want to say that it looks more like Python, but... Let's see here. Oh, no, it looks like, yeah, this looks like Java or C. It looks a lot like JavaScript. Sort of. It's sort of in its own category. It does look like Java, though. with some oddities to it. Look, there's a generic here, and it's anyway, it's structured a lot more for visual programming. Processing, it's very easy to make shapes and lines and colors and all that kind of stuff. It goes, well, either one, really. That's an excellent question, though. When you program what we just did, does it go with the sprite or the stage? Does it matter? No, it does not, actually, because the important thing here, obviously, is when the green flag is clicked. It needs to be tied to something in the Scratch program, but it doesn't matter whether it's the sprite, the cat sprite that the sprite or that the Scratch program, like an empty Scratch file comes with, or the background that the cat sprite is sitting on. It doesn't really matter there. The important thing is that it just exists on one of those and you have the one green flag is clicked, because wherever it is, whenever the green flag is clicked, it will run. And hopefully, if you're able to follow along at home and do this at home, you got a blinking LED. So how might we make the LED blink faster or slower then? Yeah, we just change the amount of time that's listed in the wait command. Yeah, exactly. So we could change it down to, like Ved said, like half a second to make it blink faster. We could change it to 2 seconds to make it blink slower. The important thing is those are the specific commands which control the speed at which the LED blinks. Uh, and that's, you know, this is all important stuff to know, not in and of itself, but it's important to be able to think about the individual commands that go into a program and how they sort of influence how the program runs as a whole. So we think about the individual wait commands and be like, okay, so how does that change how the program flows as a whole? That kind of thing, Let's see what else we got here. Okay. I guess as a thought experiment, how would we do something like this? Let's say we had two LEDs hooked up. How would we make them blink independently of one another when one LED is on, the other one is off? What would, on the hardware side, what would they need to be hooked up to? Yeah. Yeah, different pins, different GPIO pins. And then on the programming side, what would be different? Well, you already know that, but what would be different about the programming side of things? So if we were to look at this, what would be different about it? Well, we could essentially update this program with two additional commands. Yep, exactly. It would be set to the opposite of whatever. So let's say we had it hooked up to GPIO 2. We'd broadcast GPIO 17 on and broadcast GPIO 2 off. Then we would wait 1 second, broadcast GPIO 17 off and GPIO 2 on, and then wait 1 second. And that would be, on as far as the forever loop is concerned, that would be what we would change. We would also need another command on top of that. And what do you think that would be? It's the bulk of the change to the program, but what would be one more command we would need to include in order for this to operate properly? It's not an if block, although I like the fact that you're thinking about that, because we know exactly how we can predict exactly how this program would operate, and that would be turn one on and turn the other one off. So we wouldn't need to, you know, check on the status of one of the pins in order to be able to affect the status of the other pin. We just set one on, set one off, set one off, set one on, just like that, just straightforward. But there is one command in particular, and I'll give you a hint. It's a very big hint. It's outside of the forever loop. Yep. Well, I mean, these are all broadcasts, but broadcast what? Yeah, Ben's got it. We would need to set Gpio 2 or 18 or whatever to be an output pin. So we would need a config Gpio pin number out. So all in all, we would be adding 3 lines to this. We'd add another config line, so it would be config 2 out in my hypothetical example. Then we go into our forever loop. It would be broadcast 17 on, broadcast 2 off, wait 1 second, broadcast 17 off, broadcast 2 on, wait 1 second. And that would be it. Just by updating it in that way, our program would be able to handle 2 LEDs blinking at opposite intervals. Whenever one is off, the other one is on. And they would switch. And that actually does it for the first physical computing lesson for Raspberry Pi. We've got another one. But I believe actually only one more physical computing presentation for the Raspberry Pi. No, it's not just the 2 of you, although you guys, I've got like 2 or 3 people who are pretty communicative in the question box, which, I enjoy. If you oh, we've got 3 more. No, we don't. Yeah, that's true too, Ed. But hey, again, I like the fact that you guys are talking. It's nice. It lets me know that you guys are listening and you're thinking about the answers to these questions and responding and stuff like that. So, that's always good. What is this? Let's see what this is going to be. Aha, I see what this is going to be. Okay, so this is the second physical computing presentation. And this actually will be the last Raspberry Pi one we have. So maybe if we end up having additional time, we're going to do a chain of LEDs. No, unfortunately not. Not planned in these lessons, although I highly encourage you to do that if you're so inclined, because you could make some cool looking stuff. You could go to, let's see here, Raspberry Pi physical computing, because I haven't really found anything specifically for it, but that doesn't mean that I haven't that doesn't mean I've looked a whole lot. We've been using these presentations So I'll take a look and I'll see if I can't find some good sets of resources. How to connect the Pi to the computer running Scratch. Well, the Pi is its own computer, so you would need to be running Scratch on the Pi. I am using a mechanical keyboard. It's wonderful. Um, yeah, no, if you like the Pi is its own separate computer, so you would hook up a keyboard and a mouse and a monitor to it, and it'd be running its own operating system and everything like that. Yeah, it should come by default with Scratch on it. Yeah, for sure. Yeah, it's just part of what's included in the Raspbian operating system. Um, off the shelf certainly. But yeah. Also, it should be possible to actually get that stuff onto the Pi if you can connect it to a network as well, in case it doesn't come with it. So, I don't know why they keep doing this. Output is one word and the P is not capitalized. Sheesh. So as we know, these are our Raspberry Pi GPIO pins, or general purpose input-output pins. It wouldn't be GPIO input. That wouldn't really make any sense because then it would just be input. Anyway, GPIO pins are general purpose input-output pins. We're all familiar with these. You don't need me to explain exactly what those are. But let me just give you a taste of what we're going to go over for the next couple of lessons. It's going to be a button and an LED. So, what exactly could that be? We're going to be going over input. We're actually going to be... Oh, that LED is bent. Anyway, we're going to be, pressing a button to activate the LED. However, the thing is it's going to be going through the Raspberry Pi. So the Raspberry Pi is going to be listening for a signal from that button, and then we're going to do something with that button in the code in order to make an LED turn on. Yeah, essentially. One button press, GPIO 17 on. So it'll be listening as well as broadcasting. This is the other half of physical computing. You can I keep referring to everything as the other half. There are two halves to physical computing, the coding side and the hardware side. There are two halves to physical computing, the input side and the output side. But, depending upon your perspective, they're both true. So this will be the other half to physical computing, the input side. So we'll be figuring out how to write code that can account for input on the Raspberry Pi. In addition, not only will it be listening for input, it will be changing its output based on that. Once you understand that, there's a whole lot you can do with physical computing. You just need to, familiarize yourself with components and um, basically get comfortable with using them in a circuit. Things like, motors and switches and diodes and potentiometers and uh, inductors and speakers and more LEDs and LED arrays and LCD displays and whatever. I'm starting to ramble now, but these are the fundamental bits to understanding how the Raspberry Pi will communicate with the outside world. Because it's not much communication if the Raspberry Pi only talks in an output sense. You need to be able to also understand, the environment. You be able to respond to the environment in some fashion or another in order to get more complex, setups. So that's what we're going to spend next Tuesday going over, is we're going to build this circuit, and then we're going to code this circuit, and hopefully that should be fairly illuminating as far as physical computing is concerned, and Scratch and stuff like that. This is not a whole lot as far as additional, like, this is not a whole lot as far as new and unexpected concepts with Scratch is concerned. We covered a lot of that when we were going over Scratch as an introduction anyway, like a lot of the basic programming concepts and things like that. However, it is still new information because it's how Scratch relates to the physical computing on the Raspberry Pi, and that can be, well, it's a necessary thing to know. It can be very useful. So with that, though, I'm going to go ahead and do the poll questions and the question and answer time, just to give us as much time as possible to get the circuit built on Tuesday and get that all ready to go. But yeah, I could spend some time doing that on Tuesday, definitely. Just remind me about it, and that way we can talk about it a little bit. But yeah, the question was about pull-up resistance. But okay, so why don't I go ahead and do the poll questions, and then we'll spend some time doing question and answer, and then I'll have to break for my high school class, but you know we'll try and fit in as much time as possible. But anyway,